Okay, folks, let's get started. Lecture 3. Again, we will be looking at the various methods that you will be using at the level of the end user of the corresponding software. So not many derivations, just explanations and really hand-waving exploration of what it is that you could use, in which circumstances, for what reason. So as you remember from the previous lecture, Hartree-Fock was not a good approximation in a lot of cases because there may be multiple orbital occupation patterns that are required to describe a particular transition state. There may be excited states contributing significantly to the mix, and so we realized at that point that if we take a sum over the ground state, then all possible single excited states with some coefficients, all possible doubly excited states, and so on. And we apply the variational theorem to the coefficients of this expansion, then we do get, in fact, the exact solution of non-relativistic Schrödinger's equation. And that was very expensive because the number of these excitations goes combinatorially and also rather awkward to implement because you have to keep track of, for example, the normalization of this wave function. And also it wasn't immediately apparent which excitations are important and which are not. So as this linear combination goes, it was a serviceable solution, but a fairly expensive one. People in perhaps the 50s in the nuclear structure theory and in the 60s and the 70s in electronic structure theory have started applying the theory of Lie groups to the same problem, and they realized that any wave function in a Hilbert space of a particular molecule is a unitary transformation away from any other wave function. So the physicists would know what it means. For the chemists present, it is the transformation that preserves the norm on the complex space. So the equivalent of a rotation that we have in real space, but in a complex space of these wave functions. So you can easily demonstrate that any valid wave function is a unitary transformation from any other. In particular, you could say that if this is our Hartree-Fock ground state, so this simple thing here, then the true exact solution of Schrödinger's equation would be also some unitary transformation away from this, and we don't know what this unitary transformation is. However, what group theory in physics tells us that every unitary transformation is a matrix exponential of some other matrix which is anti-Hermitian. So again, a reminder, a Hermitian matrix like a Hamiltonian is when the conjugate transpose is equal to itself, and in this case the conjugate transpose has to be equal to minus itself. Well, if we look through the group theory textbooks, we realize that every unitary operator must be an exponential of some skew Hermitian operator, and the exponential for a matrix is just a Taylor series, so for the corresponding function. Now this is called a Lie algebra of a group, so that's the group, and the generators that map into the group by the exponential action are called the Lie algebra. And if you go even deeper into group theory, you realize that algebras are spanned by linear combinations of other operators called generators. And in our particular case, if you work through the math, you would realize that these generators here correspond to operators that cause single excitations, double excitations, and so on, with some adjustable coefficients. So in essence, we have a different reformulation of configuration interaction. Previously, we were adjusting the coefficients here directly in this linear combination. Now we are adjusting the coefficients of the generators of the transformation that takes us from the ground state to this exact solution. I will not go into the deep details as to why that is a better idea. These two, Anu and Luke, have published a paper on the subject and do know why that is a good idea, but in all cases parameterizing the Lie algebra is a much better idea than parameterizing the Lie group for mathematical and computer science reasons. And so if we start adjusting these coefficients of the excitation generators, then exponentiating and acting on the ground state, then we do get a better solution. And then these excitation operators, of course, have multiplicative relations. If this produces all the double excitations from orbitals I, j to a and b, then if we apply it twice, we will have to act by the square, and then we literally just take the square of this sum, and it comes like this. So the squares, the products, and so on are all straightforward, and I'm only giving you the fastest possible overview of this. Physicists have had Lie groups in their particle physics. Chemists unfortunately did not, so you would have to take my word for it. But this is a different parameterization of the configuration interaction called coupled cluster theory, because these things have cluster expansions, that performs better, can be implemented in a more straightforward way, and requires fewer computational resources, and is also better behaved than the original configuration interaction. If we look at the performance of that, this is the root mean square bond length error against a crystallographic database where people have used X-ray diffraction to find out what the true bond length is. If we look at Hartree-Fock in a moderate sized basis set, you can see the average error is about 0.02 angstrom, which is quite significant. In fact, if you increase the basis, the error even becomes worse, right? Only the energy is guaranteed to become better. But then if we try perturbation theory in the same basis set, the agreement improves, so the deviation becomes smaller. And if we use either the configuration interaction or the coupled clusters, then the agreement improves a little bit further. And in fact, this little residual isn't even dominated by the electronic structure theory method. It's dominated by the vibrational averaging, because of course every real crystal at ambient and even 0 Kelvin would to some extent vibrate. If we look at the energy errors, so this is atomization energy. This is somebody literally over the course of chemical history with a heat bath and this bomb calorimeter, for example, burning things and finding out how much energy is released. And then we can calibrate the performance of all these methods against those databases. And, 85 kilocalories per mole is a disastrous error, right? Chemists would know what this means. This is actually the energy of a typical chemical bond. So this is dead wrong. When you get to a much bigger basis, it becomes less dead wrong, but still dead wrong. When you start including electron correlations through perturbation theory, it becomes slightly less dead wrong, and here is the big difference between configuration interaction and the coupled cluster. So this is just singles and doubles, and this is single, double, and perturbative triple excitations, that this is actually getting to somewhere that resembles the chemical accuracy. So as you go up the hierarchy of both the basis set and the sophistication of how you account for electron correlation, the performance improves, at least on the energy here. We can look at the difference between the coupled cluster energy and the full configuration interaction energy for a tiny molecule, in this case water in vacuum, where we can actually on a large supercomputer afford to solve Schrödinger's equation exactly, and then we know the true energy to all the decimal places. And you can see that if we include single and double excitations into the generators of the coupled cluster method, we get significantly better, 3 or 2 orders of magnitude better than the restricted Hartree-Fock. Another order of magnitude if we include triple excitations, another order of magnitude quadruple, and another order of magnitude if we include 5-fold excitations in there. So you can see a really rapid convergence to the exact configuration interaction energy, at least for a tiny molecule. Remember what I told you about the size consistency error in configuration interaction? When we put the two molecules together, they can excite into each other's orbitals, and so there is an unphysical attraction between them as a result. That effect is absent in the coupled cluster method. It is strictly size consistent. So if you put two molecules together, the total energy of the two of them is exactly the sum of the individual energies of the two molecules, which is another useful side effect of treating the excitation process group theoretically. And of course, complexity scaling is a disaster. It always is with these configuration interaction type methods. If you have 100 orbitals in your calculation, then 100 to the 6 is perhaps just about manageable. 100 to the 7th starts being, you know, an overnight, over the weekend, and never complete kind of calculation. So unfortunately, these methods, precise as they are for non-relativistic quantum mechanics, they tend to scale really badly. There is a huge amount of work that is being done, in particular in MolPro and Orca packages, to improve the scaling by aggressive screening of the integrals, not computing them, using those resolution of identity methods I had mentioned in the previous lectures, and cutting various corners. So in some very good packages, I think they now got it down to quadratic, but a lot of conditions have to be satisfied for that to be possible. But always read the manual. There are packages that pride themselves on highly efficient implementation of these methods, and if you find yourself needing to use one of those, then find out which package has the most favorable scaling implementation of it. Okay, so a couple of slides of the summaries of all the post-Hartree-Fock methods. Once again, a single determinantal wave function, that's the technical term. The chemical term is a single orbital occupation pattern, is in a lot of cases not a good approximation to the true ground state of the molecule, and so we need to correct it further. We can correct it with perturbation theory, in which case this is Möller-Plesset type methods. We can correct it by just taking linear combinations of all possible occupation numbers, either by a straightforward linear combination, in which case it's called configuration interaction, or by a fancy group theoretical ansatz, in which case it's called coupled cluster. And here you can see why people prefer coupled cluster these days. If you take singles and doubles, that recovers 96% of the correlation energy in the beryllium atom, but 99.7% in the case of coupled cluster. And so by the time you include triples, either perturbatively or into the excitation process, you're at 99.99% of the correlation energy, whereas the straightforward coupled cluster is still not converged, but at quadruples, of course, pretty much you are done. And then Möller-Plesset is not a variational ansatz, it is perturbation theory, so it is the energy here is not an upper bound. It is entirely possible to even overshoot it a little bit, but then of course MP8, MP9 and so on will bring you closer to 100%, although not necessarily monotonically. And again, the standard health warning, these all use single reference, so they take a particular orbital occupation numbers and they attempt to improve, either perturbatively or with various linear combinations. These methods will fail in situations where the initial molecular geometry or some kind of intermediate is very significantly multi-determinantal, multi-state. For example, bond cleavage situations and isomerizations of double bonds often are, and then you need to use multi-reference versions of these methods. That's an example of dissociation of hydrogen fluoride molecule in vacuum. If we look at the methods here and at the curves in there, the correct curve is black. So when you push the atoms into each other, of course the energy rises because they repel. Then that's roughly the equilibrium bond length. I think that's just relative to the true bond length, so this is 1. And then when you pull them further apart, they first resist, but then the bond breaks, and you've got this asymptote at the energy of the individual uninteracting atoms. If we are not careful about how we treat that, so for example, CCS dt from the bound reference state would have a non-physical repulsion between them at long distances. CCSD would have extra non-physical attraction, so the barrier height would be slightly bigger. And if we actually use the multi-reference state, so for the both spins up and down in there, then this is the correct curve. And if we use a complete active space configuration interaction with just the bonding and the anti-bonding orbital without including extra excitations into account, we do get the correct asymptotic behavior and a reasonably correct barrier, but of course the entire thing is somewhat further up in energy because this has very little variational freedom, and so it's an overestimate, although the differences are probably pretty accurate here. So read the literature, find out which combination of which methods works here, because it is impossible to solve the equations exactly in most cases. You would have to find out which methods work best. There are situations where the error of the method is not in fact even present in the Hamiltonian that you have. If you look at d elements like cobalt and various exotic interactions like cobalt-phosphorus bond, which really includes significantly d orbitals, you would realize that in that case a lot of the effects in the electronic structure theory are produced by the spin-orbit coupling. So cobalt is a heavy element, and so is phosphorus. You've got d orbitals involved there, and spin-orbit coupling simply isn't present to begin with in any of this. And so if you look at the pattern of how much more accurate things get, you would see that, well, okay, Hartree-Fock's pretty wrong, right? So 7% average deviation on the geometries. So these are bond lengths in angstroms and angles in degrees. It does improve with MP2, for some reason gets worse with coupled cluster, but in this case the error is really dominated by relativistic effects like spin-orbit couplings that are not even present in the original Hamiltonian. And at the point, if you want it to be a bit more accurate, then this is far beyond the content of our simple course here, and how to include the spin-orbit coupling and various other related relativistic effects. So that's the grand table of the scaling, and the scaling here refers to the worst possible naive implementation of the corresponding methods. There are software packages that do much better than this. In fact, I think Gaussian is almost linear these days on the Hartree-Fock, assuming your molecule is big enough. MP2 probably got knocked down to quadratic in the latest software, likewise for the singles and doubles coupled cluster, but this is the worst possible scaling to give you an idea of the expense of all these methods. Realistically, these days, on the sorts of workstations you have on your desktops, you will be able to do a couple of hundred atoms with just the Hartree-Fock, and also response derivatives to magnetic fields, to electric fields, to atom displacements, and so on, analytically, so reasonably quickly in that case. For MP2 and MP4, up to 100 atoms on the best current software. For MP2, up to 20 on MP4. Good packages have first and second analytical derivatives for MP2, but MP4 we have to use finite differences, so just use finite field or finite atom displacement and then look at how things change. For coupled cluster and configuration interaction singles and doubles, again up to 20 atoms, usually analytical derivatives are available. And full configuration interaction, if one must insist, 3 or 4 simple atoms at best is what currently can be done, and the derivatives would need to be done numerically in that case. That's the final summary slide about the distributions of errors across a large database for the various properties. And this is quite a useful thing to bear in mind. So this is deviations in picometers for the average bond lengths from X-ray geometries as a function of the level at which we account for the electron correlation. So that is the true bond length here at 0. Hartree-Fock is this broad bell. You can see there is the systematic error, a significant one, and a large scatter around that. If we start using Möller-Plesset corrections, then we get systematic error in the opposite direction, and the scatter is smaller, and also the error is smaller. Coupled cluster with singles and doubles in the excitation generators are spot on the average, and the deviation is also a little bit narrower. And interestingly, because bond length is not energy, so it's not guaranteed to improve, if you include perturbative corrections for the triple excitations to it, your average gets worse, and your standard deviation, I think, is slightly better here. So better standard deviation for an incorrect average. So be prepared to look through the literature. In this case, if you are fishing for molecular geometry, CCSD is probably the better idea in this case, but it is hard to say why. Maybe it's some kind of error compensation. The fact that it doesn't do vibrational averaging got compensated with the fact that it got the energy slightly wrong. The two errors have cancelled themselves. You apparently get the right answer, right? So some right answers are produced for the wrong reason in this case. That is the same as a function of basis set size. Thankfully, that is pretty straightforward, the conclusion here. If you use a double zeta basis, you get a large error and a large scatter. Triple zeta, smaller error, smaller scatter. Quadruple zeta, even smaller error, even smaller scatter. And finally, quintuple zeta, I think, in there. Or the polarized core, so but basically extra functions on the quadruple zeta basis set, you can see that it has arrived to the correctly centered and reasonably narrow distribution. So at least with respect to the basis set size, the bigger the better appears to be holding in this case. And that's a dissociation curve. Again, the same wisdom about restricted versus unrestricted. The correct curve saturates and just reaches a constant here for the non-interacting atoms once you put them far away from each other. And if you are not using the unrestricted reference state, then you get this unphysical repulsion at large distances between those atoms. So this is simply an indication that the wave function has a significant multi-reference character, and so high order configuration interaction or a multi-reference ground state is necessary there. So beware of these various error compensation situations, and always check the literature about what is the best method for the particular property that you use. Okay, so summary of Hartree-Fock and post-Hartree-Fock. Fast approximate methods, these two double zeta basis sets, both here and here, with small sets of polarization functions, will get you the geometry that is not ridiculous. All right, chemically it will be sensible, but only qualitative. Möller-Plesset will get you to chemical accuracy, likewise CCSD or without the triples in here. If you really need very high accuracy energies, then use those. And there are extra specialized combination methods that use linear combinations of these things to further reduce the energy. So Google these things up. These are highly specialized for extremely accurate thermochemistry. Mentioning John Popple here, who got the Nobel Prize for the exploration of all the computer science and chemistry behind it. Energies, in fact, can sometimes even be extrapolated to the infinite basis set. So if you take a double, triple, quadruple, and so on zeta basis sets, of course, they will approach systematically your asymptotic energy in the infinite basis set limit. So you can just put the zeta number into here and then extrapolate it to infinity once you've fitted this coefficient to a couple of energies that you have computed, and so that is called the complete basis set limit. Okay, so this is the classic early electronic structure theory that attempts to solve Schrödinger's equation systematically. There is a radical alternative to these methods that is based on densities. And before we go deeper into it, we need to look at what density even means. Of course, you know Copenhagen interpretation of quantum mechanics, that the absolute square of the wave function is the probability density. And so if we have a particle, we take norm squared, and that's our probability distribution for a particle. If our particle is an electron in a molecule, of course it's just one electron, and so we need to integrate over the coordinates of all the other electrons, but thankfully this is fully symmetrized, anti-symmetrized, but it doesn't matter for the absolute square with respect to all of the particle identities. And so we take the first particle coordinate here and we integrate over all of the other particles multiplied by the number of particles, and that is our total electron density. And this is how it looks. This is isodensity surface, so the surface of equal probability density mapped with the electrostatic potential. So you would have just an electron cloud sitting around the nuclei because it is attracted to those nuclei, but it repels itself, and so a certain equilibrium is then displayed. Then the spin density, of course, is just the difference between the density of spin up and the density of spin down electrons, and the charge density, because every electron is charged exactly the same as every other, is just the electron density times the charge of the individual electron. Now, why would we want these densities beyond making pretty pictures and making chemical conclusions? That is because we can do a bit of philosophy initially. Imagine we know the ground state electron density. The density through Poisson's equation, as you well know, determines the potential in which that density sits. So we do know, therefore, the potential. If we do know the potential, it means we do know where the nuclei are, because they are creating this potential. And of course, we do know the kinetic terms. They're just mv squared over 2. And so we do know the potential and we do know the kinetic terms. That means we know the entire Hamiltonian of the system. And as soon as we know the entire Hamiltonian, we know everything about that system, because the Hamiltonian can be diagonalized, we obtain the wave functions, we take the expectation values. So in principle, at least philosophically, if we do know the ground state electron density, we potentially know all properties of the system. But of course, the density is a three-dimensional object. It is much simpler than the 3n-dimensional wave function. The wave function is three-dimensional with respect to every electron there is. And that's just the total electron density, which is just 3D. Easier to store, easier to work with, but well, that's a bit non-constructive. It doesn't even tell us, right, how to obtain this external potential, how to reconstruct this Hamiltonian. We don't know anything here. But we can say that, okay, the basic lemma of this density functional theory is the ground state density here of a bound system of interacting electrons in some potential determines this potential uniquely, and that seems to be the case. So if we manage to reformulate our quantum chemistry in terms of three-dimensional electron density, we will probably simplify it an awful lot. Well, this is the other winner of that Nobel Prize for electronic structure theory. It was Popoul and Kohn. And Walter Kohn proved a theorem that there exists a well-defined functional of electron density, which does have a global minimum at the ground state density. So the variational theorem does still apply in some sense to this density formulation. And this was how we calculated the things in the conventional quantum mechanics. If we do have our exact known ground state wave function, then that's the Hamiltonian, so kinetic energy, nuclear potential, and inter-electron repulsion terms. We take this expectation value, that's our energy, and at the ground state, this energy attains a global minimum. Using this Hohenberg convariational principle, we could say that the same could apply to the density. That there would be the energy, which is a functional of our density, the kinetic functional, which we do know because it's quite easy, p squared over 2m. Then inter-electron repulsion functional, which we don't know. And the nuclear attraction, which we also do know, because if we know the density, we know from standard Coulomb integrals what is its attraction energy to the nuclei. So we do know this term, that's just mv squared over 2. We do know that term, that's just straightforward Coulomb interaction, but we don't know exactly, given all the quantum mechanical complexities, what goes on with this inter-electron repulsion, because we don't know inter-electron details, because we just see the total electron density. So what can we do about this? Well, let's start in the same way as we had started with the Hartree-Fock theory. We will create a bunch of one-electron orbitals, and orbitals here comes in quotes because these things are a basis set in the mathematical sense. They might not even have the physical meaning in the same sense as the Hartree-Fock orbitals had, because this is not a solution of Schrödinger's equation, it's a solution of something else. But still, we can do that. We can say, okay, our case one electron orbital will be a linear combination of some basis functions with some complex coefficients. And then if we take the absolute squares and sum them up, that will be our total electron density. Okay, this is how we did that for Hartree-Fock. That should be epsilon. The fonts got messed up on the university computer. That's our kinetic energy term, that's the potential term, which we didn't know in the previous slide. That's our orbital, the energy, and then the orbital again. So what do we do with this potential energy term? Well, we take it apart. And take a good look at the parts of it which we can compute, which we can fudge, and the parts that we don't know at all. So this potential energy of those moving electrons will include straightforward things like nuclear attraction. So that's the nuclear charge, that's the density of the electron cloud, that's the distance to the nucleus, and this is literally just Coulomb interaction and a sum over all nuclei. Then we do have inter-electron repulsion, a half to avoid the double count. Then we have the pair density of the electrons, the inter-electron distance, and then the integral over the coordinates. And then, of course, there should be a sum here over all of the electron pairs. But because we are looking at an individual one-electron orbital, so it's electron 1 and then electron 2 and the integral over. And then there will be all of the inter-electron correlation and also Coulomb exchange terms here, which we do not know. And so the revolutionary proposition in the 60s, when this all came about, was to say, well, we don't know this, we might never know this, why don't we fudge something up and see if something works? And so people started proposing various physically plausible things, starting really from just uniform electron gas and throwing things at the wall and finding out which ones of them produce sensible energy, sensible orbitals, and sensible properties. Once again, this is epsilon. So at the lowest possible level, we could say, well, okay, that exchange correlation energy might just be local. So there may exist some functional of it, some kernel of this integral. If we convolve this density with this kernel, we might get some approximation for the energy. We could say, well, okay, at a slightly more complicated level, we could say that not only does this energy depend on the density itself, it might depend on the slope of the density, so gradient, how rapidly it changes, and that's called a generalized gradient approximation. So again, there are many possible mathematical expressions for this, but in general it would depend on the density and its gradient. And so on. We can add the extra higher derivatives, we can add other properties of this density. There's a giant zoo by now, perhaps at least of a few hundred and possibly over 1,000 different exchange correlation functionals that work or don't work in some situations or other. And the true one is unknown. And the latest fashion has been to take several of them, take linear combinations, and then optimize the coefficients in those linear combinations to fit some experimental data sets. So a hybrid exchange correlation functional might have a contribution from the local density approximation, might have a little bit of Hartree-Fock exchange, might have a little bit of local density approximation exchange, some generalized gradient approximation for the Coulomb terms and correlation terms, and so on. And these coefficients are unknown and are simply found by fitting to experimental data, which is why density functional theory doesn't, strictly speaking, qualify as an ab initio method. It doesn't solve Schrödinger's equation, and it does have empirical parameters that have just been found by fitting them to some big thermochemical or other property database. That's an example of reaction barriers, and these abbreviations are different exchange correlation functionals. Chemists must have heard about B3-LIP by now, at least it's been pronounced to you somewhere. The paper that introduced BLIP got cited over 100,000 times because everybody started using these things. This was the first one that was really huge general success. And if you compare DFT with high-level ab initio reaction barriers, you can see that it's not awful. All right, the exchange correlation functionals, even in 1997, got close to the ab initio reaction barriers, to within a few kilocalories per mole, which is really quite good. And then if you look at the optimized geometries, again, that's the deviation on the bond lengths in angstroms and on the angles in degrees. You can see we are pretty much close to what would be reasonably called chemical accuracy, because by the time you're at 0.01 angstrom, that's actually pretty good. Once again, these exchange correlation functionals, they work for some things and don't work for others. Check the literature for what works best in your particular case. A particularly treacherous territory is magnetic resonance chemical shifts. Some methods get them dead wrong, and others are spot on for reasons that are mostly the wrong reasons, so some cancellation of errors in there. That's some more performance. So the mean absolute error and the maximum absolute error on the G2 database of energies. And these are, again, various exchange correlation functionals. You can see some are awful and some are pretty good. That is for the bond lengths, likewise. That is atomization energies, likewise. So there's an hierarchy. Some of them are really awful, and there's systematic improvement, at least as a function of the year in which the corresponding paper has been published. And until very recently, Axel Becke, so the B in B3-LIP, his paper was the most highly cited paper in the history of science. In the last couple of years, that's unfortunately untrue, because the machine learning people have taken over, and the Adam algorithm for the neural network training has now collected, I think, 130,000 citations. That's a testament really to how useful these things in practice are. Another table, in this case for ionization potentials, again you see systematic improvements, and this is a table that gives the average error, the error over the main group, carbon, oxygen, and so on of the periodic table, main group energies, and these are transition metals. And you can see there is a certain hierarchy of the functionals. Some of them are dead wrong for transition metals, but extremely good for the main group elements, so highly optimized for a case-specific scenario. And there is this very recent one called MO6 that is uniformly pretty good for everything, at least as energies go, but it has recently been demonstrated that its densities are probably not the best ones possible. So once again, check the literature for what works in your case. The final thing to notice about DFT is that it's unfortunately got a problem with asymptotics, so long-range interactions. When we did Hartree-Fock theory, we had Coulomb and exchange interactions in there, and this is the example of the exchange term from that Coulomb part. And you can see that's our densities, and these are Gaussians in our case, and this 1 over r is the asymptotic dependence of the Coulomb interaction. So if you take two charges at a large distance, at large distances when they look like point charges, the interaction scales as 1 over r. Unfortunately, for density functional theory, a lot of these exchange correlation functionals absolutely do not have this kind of scaling. If you look at the local density approximation exchange functional, it's just some power of the density integrated over. If you look at the more sophisticated ones, well, they've got the LDA part, and they've got this strange part, which is the function of the gradient of the density, but not much else. Again, this would asymptotically be incorrect, and then it would enter these hybrids, and so the hybrids would have an incorrect asymptotic Coulomb interaction. So B3 lib, for example, asymptotically decays as 1 over r over 5, right, which is, of course, chemically incorrect. And so what people started doing is producing these range-separated hybrids where we take 1 over r and we split it up. This is the error function from statistics, and what this simply does is it splits the Coulomb interaction from the nearby component and the distant component. But ultimately, this is not an approximation, this is a correct thing, because this error function just cancels. And that's just the integral of the Gaussian, so it's a function that starts off at 0 and then becomes 1, and that separates us some distance away. And so we can use it to make the balance between the Hartree-Fock part of B3 lib. It's a mixture of Hartree-Fock and DFT, distance dependent. So we could just attenuate DFT completely and have Hartree-Fock at infinity, which has the correct asymptotic dependence for the Coulomb interaction, or we can have some coefficients so that the fraction of the Hartree-Fock is distance dependent. And again, these coefficients are empirical, and they become necessary in situations when you're dealing, for example, with non-covalent complexes where long-range interactions are necessary. But the best way of dealing with them, as you can probably already kind of realize here from the fudge, that this is that configuration interaction of beta coupled cluster, which is size consistent, is probably a better way of dealing with non-covalent complexes than density functional theory. There are all sorts of other empirical corrections, but ultimately it's not a good mechanism for dealing with them. Okay, so the summary of the lecture: we have looked at a different way of doing configuration interaction, a more group theoretically consistent method called coupled cluster, in which it's not the straightforward linear combination whose coefficients are optimized, it's the entire excitation process, the generators of which are being optimized, so the coefficients there, and it scales better and it performs better. We then looked at the long list of tables for the performance of all of these things, the take-home message being that real-life performance of this enormous bestiary of methods, basis sets, and so on is essentially impossible to guess. So, but thankfully there is a huge volume of literature about which method works best in which particular situation, so go there. And then we introduced density functional theory, which for most practical chemical purposes is what you are going to be using. It's got decently accurate energies, geometries, and magnetic properties, at least for CH and O molecules, and a much better complexity scaling, because you are dealing not with ON to the 7th, ON to the 8th post-Hartree-Fock correction to multi-dimensional wave function that contains coordinates of every particle. You do instead just have the 3-dimensional density, and then the complexity scaling of that is pretty much uniformly subcubic. So cubic in the worst case, quadratic if you've programmed it well, and even asymptotically linear if you've programmed it really, really, really well. And I'm examining a PhD student from a friendly lab actually in the afternoon, and his work is about linear scaling density functional theory, which is necessary if you've got huge slabs of materials, for example, and periodic boundary conditions and so on, with many hundreds of atoms, and then you need all of that stuff. Okay, so this finishes our exploration of how to compute an energy, and from the next lecture we will look at what to do with that energy once you have computed it. So geometry optimization, properties, and the rest of the stuff. Any questions?